Gravity shapes the universe. It guides planets around stars, anchors galaxies, and dictates the grand motion of cosmic structures. Yet, in most places, gravity is gentle enough that we experience it as a simple downward pull. In the hearts of some of the densest objects in the universe, however, gravity becomes something far more extreme. Neutron stars are among these remarkable objects. Born from the collapse of massive stars, they pack more than the mass of our Sun into a sphere barely 20 kilometers across. Here, gravity is not just a force, it is a curvature of space-time so intense that it warps time itself and dominates the behavior of matter at a fundamental level. Understanding gravity inside a neutron star requires us to think beyond the familiar, to imagine a place where ordinary intuition no longer applies. Electrons and protons are crushed together, neutrons are packed like grains in a cosmic sandpile, and pressures reach levels that challenge our understanding of physics. In this video, we will explore how gravity acts in these extraordinary conditions, how it interacts with quantum forces, and how it shapes the very structure of a neutron star. Join us as we journey to the core of one of the universe's most fascinating laboratories. Before we continue, please consider leaving a like on this video and subscribing to the channel. Your support is greatly appreciated, and with that out of the way, let us continue. Before we can understand gravity inside a neutron star, it helps to take a step back and reflect on gravity itself. In our everyday experience, gravity feels simple. We see it as the force that keeps our feet on the ground, guides objects as they fall, and holds the moon in orbit around the Earth. Isaac Newton described it as a force acting at a distance, where massive objects pull on one another. This picture works perfectly for most situations we encounter. But when we begin to look at the universe on a grander scale, or into the extreme interiors of dense stars, gravity reveals a deeper, more subtle nature. Albert Einstein's theory of general relativity teaches us that gravity is not a force in the traditional sense. Instead, it is the curvature of space-time caused by the presence of mass and energy. Objects move along paths called geodesics, which are the straightest possible trajectories in curved spacetime. In this framework, mass tells spacetime how to curve, and spacetime tells mass how to move. This shift in perspective changes everything when we consider dense objects. Around Earth, the curvature of spacetime is slight, and Newton's equations approximate reality very well. Around a neutron star, however, space-time is dramatically curved. Gravity is no longer a gentle pull. It is a dominant feature of the environment. To fully understand it, we must think not only about the mass of the star, but also about the energy and pressure within it, which themselves contribute to the curvature. We can also consider the idea of gravitational potential. This concept helps us visualize how strongly a mass is embedded in spacetime. For ordinary stars, the potential gradually increases toward the center, and the strength of gravity generally rises with depth. In neutron stars, the story is more complex, but the principle remains. Regions with more mass energy create a deeper well in spacetime, guiding how matter and light move inside. A key point to keep in mind is that gravity acts universally. It influences everything, from particles to photons, and even pressure itself becomes a source of gravity under the rules of general relativity. This is one of the reasons neutron stars are so fascinating. The extreme densities and pressures inside them cause gravity to behave in ways that challenge our intuition. The familiar ideas of up and down, or even center and surface, take on new meanings. By establishing this understanding, we lay the groundwork to explore the interior of a neutron star. We will soon see how gravity interacts with quantum forces, how it shapes the star's structure, and how it leads to some of the most extraordinary phenomena in the universe. Appreciating gravity in this deeper sense allows us to step beyond the familiar and enter a world where space-time itself is a living, responsive stage, molded by the extreme conditions at the heart of a neutron star. To understand how gravity works inside a neutron star, we first need to consider how these extraordinary objects come into being. Neutron stars are born from the dramatic deaths of massive stars, which are at least 8 times the mass of our Sun. Throughout their lives, these stars fuse lighter elements into heavier ones in their cores, producing energy that balances the inward pull of gravity. This delicate equilibrium allows the star to shine steadily for millions of years. As the star exhausts its nuclear fuel, the balance begins to shift. Fusion in the core can no longer produce enough pressure to counteract gravity. Once the core becomes predominantly iron, fusion ceases to generate energy because iron nuclei cannot release energy through fusion. Without this outward pressure, gravity begins to dominate, pulling the core's matter inward with tremendous force. This rapid collapse is astonishingly powerful. In mere seconds, the core, which might have been several thousand kilometers across, is compressed into a sphere only about 20 kilometers in diameter. At this point, the densities inside the core reach unimaginable levels. A sugar cube-sized portion of neutron star matter would weigh billions of tons on Earth. The collapse continues until a new kind of pressure intervenes. This is neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle. Neutrons, like electrons, cannot occupy the same quantum state. As a result, when matter is compressed beyond a certain point, this quantum pressure pushes back against gravity. In addition to neutron degeneracy pressure, short-range nuclear forces between neutrons provide another layer of resistance, preventing the core from collapsing further, at least temporarily. The result is a neutron star, an object where gravity and quantum forces are locked in a delicate balance. The outer layers of the star, unable to withstand the core's sudden contraction, are expelled into space in a spectacular explosion known as a supernova. This event scatters heavy elements throughout the cosmos, seeding the universe with the building blocks of planets, life, and new stars. The birth of a neutron star is not just a dramatic transformation, it is a natural laboratory for extreme physics. The core that survives is a region where gravity is immensely strong, space-time is intensely curved, and matter exists in a state that cannot be reproduced on Earth. This is why neutron stars are of such interest to scientists. They push the boundaries of our understanding of matter, energy, and gravity itself. By examining the formation of neutron stars, we gain insight into why gravity behaves the way it does inside them. The very process of collapse concentrates enormous mass into a tiny volume, setting the stage for the extreme gravitational conditions that define these objects. In the next section, we will explore the internal structure of neutron stars in detail, examining how gravity varies from the crust to the core, and how these conditions affect the behavior of matter under the most extraordinary circumstances in the universe. Having explored the birth of a neutron star, we can now turn our attention to the extraordinary conditions that exist within these compact objects. Neutron stars are among the densest forms of matter in the universe, second only to black holes, and their internal structure is both layered and complex. Understanding these conditions is essential for grasping how gravity behaves inside them. The outermost layer of a neutron star is known as the crust. Despite being only about a kilometer thick, the crust is incredibly dense compared to any material we encounter on Earth. It is composed primarily of atomic nuclei and a sea of free electrons, arranged in a rigid lattice. Gravity here is already extreme. The acceleration at the surface can exceed 100 billion times that on Earth. This intense gravitational pull compresses matter into forms that are entirely alien to our everyday experience. Beneath the crust lies the outer core, which extends for several kilometers inward. Here, the pressure is so immense that electrons combine with protons to form neutrons, creating a fluid that is almost entirely neutron-rich. This region is incredibly uniform, yet the density is staggering. A teaspoon of this matter would weigh about 1 billion tons. The interplay between gravity and quantum forces becomes apparent here. Neutron degeneracy pressure, arising from the Pauli exclusion principle, resists further compression, providing a counterbalance to the gravitational force attempting to crush the star further. Deeper still is the inner core, a region about the size of a small city. The precise composition of the inner core remains one of the great mysteries of modern astrophysics. Theoretical models suggest it could contain exotic states of matter, such as hyperons, meson condensates, or even deconfined quarks. Pressures in this region are so immense that they surpass anything achievable in terrestrial laboratories. Gravity, already extreme in the outer layers, becomes increasingly complex here, influenced not only by the star's mass, but also by the pressure of the dense matter itself. In general relativity, pressure contributes to gravity, meaning that the inner core's resistance to compression also modifies the curvature of spacetime. Temperature inside a neutron star, while initially very high, billions of degrees immediately after formation, cools relatively quickly over millions of years. Despite this cooling, the internal pressures remain extraordinarily high. Additionally, many neutron stars possess extremely strong magnetic fields, which can reach trillions of times stronger than Earth's. While these fields are mostly external, they can influence particle behavior in the outer layers, creating complex interactions with the star's matter and contributing to the overall dynamics of the system. Gravity inside a neutron star does not behave as it does in less extreme objects. In typical stars or planets, gravity gradually increases toward the center. In neutron stars, the interplay between dense matter, quantum forces, and general relativity leads to a more nuanced picture. Gravity is strongest near the surface in some models, where the mass above exerts tremendous pull, while the interior shows complex variations due to the pressures and densities involved. Understanding this gradient is essential for predicting the star's stability, its radius, and the behavior of matter under such intense conditions. In summary, the interior of a neutron star is a realm of extremes. Extreme density, extreme pressure, and extreme gravity. From the rigid lattice of the crust to the fluid outer core and the mysterious inner core, each layer presents unique conditions that challenge our intuition. These conditions not only dictate how the star resists collapse, but also shape the curvature of space-time itself, making neutron stars one of the most fascinating laboratories for studying the interaction between matter and gravity. By examining these physical conditions, we prepare ourselves to explore the detailed gravitational profile of neutron stars, and to understand how gravity acts differently in their interior compared to any environment we can experience on Earth. Now that we have explored the internal structure of neutron stars, we can examine the most fundamental question: how does gravity behave within them? Understanding the gravitational profile of a neutron star requires us to go beyond the Newtonian view of gravity as a simple force pulling matter together. In these extreme environments, general relativity governs the rules, and gravity becomes a subtle interplay between mass, pressure and space-time curvature. In most familiar objects, such as planets or ordinary stars, gravity increases steadily toward the center. The deeper you go, the more mass lies above, pulling inward. Near the surface, the pull is relatively gentle. At the core, it is stronger, but still follows a straightforward, intuitive pattern. Neutron stars, however, challenge this intuition. Their enormous densities and compact size create conditions where pressure itself contributes to gravity. In general relativity, not just mass, but energy, momentum, and pressure all curve spacetime. This means that as we move inward from the surface of a neutron star, the gravitational field is influenced not only by the mass above, but also by the intense pressure of the matter beneath. At the surface, gravity is already extreme. A person standing on a neutron star would experience an acceleration on the order of 100 billion times that of Earth. Light itself is bent dramatically, and time passes more slowly compared to distant observers, a phenomenon known as gravitational time dilation. Despite the small radius of the star, the mass packed into that tiny volume produces a gravitational potential deep enough to trap particles and affect even neutrinos. Moving inward through the crust, gravity continues to increase, but in a way that is subtly different from ordinary stars. The rigid lattice of nuclei and electrons provides structure, resisting compression through electron degeneracy pressure. This pressure contributes to the star's overall gravitational field. While the increase in gravitational pull is dramatic, the effect is not uniform. The outermost kilometers are dominated by the star's mass above, while deeper layers begin to feel the influence of internal pressure, which modifies the curvature of spacetime. Entering the outer core, composed almost entirely of neutrons, we see the effects of neutron degeneracy pressure in full force. Neutrons resist being squeezed into the same quantum state, producing an outward pressure that partially counters the inward pull of gravity. Interestingly, in this region, gravity does not simply peak at the center. Due to the contribution of pressure to space-time curvature, the gravitational acceleration may reach a maximum somewhere within the inner layers, rather than precisely at the core. The result is a gravitational profile that is counterintuitive. Gravity is strongest at certain depths, then can slightly decrease toward the very center, despite the presence of the densest matter. The inner core of the neutron star presents the most extreme environment. Here, densities may reach several times that of an atomic nucleus, and matter could exist in exotic states such as hyperons or deconfined quarks. Gravity here is not merely pulling inward, it is interacting dynamically with the pressure and energy of the core. The Tolman-Oppenheimer-Volkoff (TOV) equations describe this equilibrium. They extend Newtonian hydrostatic balance into general relativity, accounting for how pressure contributes to gravitational mass. The solution to these equations reveals the detailed gravitational profile, a balance where the immense gravity of the star is moderated by quantum and nuclear pressures, allowing the star to maintain stability. This intricate balance explains why neutron stars can exist without immediately collapsing into black holes. However, the TOV limit sets a hard boundary. If the mass of a neutron star exceeds roughly 2.2 to 2.4 times that of the Sun, gravity overwhelms all resistive forces and collapse into a black hole becomes inevitable. Below this threshold, the star remains stable, a testament to the remarkable interplay of forces at work. The gravitational profile inside a neutron star also affects observable phenomena. The bending of light near the surface alters the appearance of the star. While time dilation affects signals received by distant observers, neutrinos and gravitational waves emerging from the star's interior carry imprints of the star's gravity, offering scientists indirect ways to probe these extraordinary conditions. In summary, the gravity inside a neutron star is a complex, dynamic feature, shaped not only by the star's mass, but also by the intense pressures and quantum effects within. Unlike the simple picture of gravity we experience on Earth, here it is a nuanced interaction of matter, energy, and space-time curvature. From the crust to the core, gravity reaches extreme magnitudes, bends light, slows time, and dictates the very structure of the star. It is a phenomenon that challenges our intuition and expands our understanding of how the universe organizes itself under the most extreme conditions. By examining this gravitational profile, we are prepared to explore the role of pressure as a source of gravity, and how quantum forces and nuclear interactions counterbalance the immense pull, allowing neutron stars to exist as stable yet extraordinary objects. In most familiar situations, we think of gravity as being generated solely by mass. On Earth, the weight of an object depends on how much matter it contains. In neutron stars, however, the picture is more subtle and profound. Under the framework of general relativity, pressure itself contributes to gravity. This means that the immense pressures inside a neutron star are not just resisting gravity, they are actively shaping it. To understand this, it helps to recall that gravity, in Einstein's theory, is the curvature of spacetime caused by energy and momentum. Mass is one form of energy, but pressure is also a form of energy density. In the extreme environment of a neutron star, where matter is compressed to nuclear densities, pressures reach such staggering magnitudes that they become a significant source of spacetime curvature. The higher the pressure, the more it adds to the gravitational pull within the star. Consider the inner core, where densities are several times that of an atomic nucleus. Here, neutron degeneracy pressure resists further compression. These neutrons cannot occupy the same quantum state due to the Pauli exclusion principle, creating an outward pressure. In Newtonian physics, we would consider this pressure simply as a counterforce to gravity. In general relativity, however, the pressure also contributes to the star's gravitational field. The very pressure that prevents collapse simultaneously increases the curvature of spacetime, subtly modifying how gravity behaves at different depths. This creates a fascinating feedback loop. As matter is compressed, pressure rises, which strengthens the local gravity. That gravity then pushes back, compressing the matter further. The equilibrium of a neutron star is therefore a delicate balance between gravitational forces, pressure contributions, and the fundamental quantum properties of neutrons. The Tolman-Oppenheimer-Volkoff (TOV) equations mathematically describe this equilibrium, combining mass, energy, and pressure to determine how gravity varies throughout the star. Solving these equations reveals that the gravitational acceleration inside a neutron star does not increase monotonically toward the center, as one might expect, but instead reflects the complex interplay of mass and pressure. Understanding pressure as a source of gravity also helps explain why neutron stars can maintain stability at such extreme densities. Without this contribution, the balance between gravity and internal forces would be different, and stars of similar mass and density might not be able to exist without collapsing into black holes. The interplay between pressure and gravity ensures that neutron stars have well-defined radii and masses, and it determines the maximum mass a neutron star can support before collapse. In essence, pressure in a neutron star is not just a resisting force. it is an active participant in shaping gravity. This concept challenges our everyday intuition, reminding us that in the universe's most extreme environments, familiar ideas like up, down, and center are less meaningful than the intricate relationships between mass, energy, and space-time. By appreciating this, we gain a deeper understanding of how neutron stars remain stable and how gravity, in combination with quantum mechanics, sculpts the structure of one of nature's most extraordinary objects. Inside a neutron star, gravity is unimaginably strong, but it does not act alone. To understand how these stars resist total collapse, we must explore the counteracting forces at play, quantum forces, and how they balance the immense pull of gravity. This delicate equilibrium is one of the most fascinating aspects of neutron star physics. The first quantum force to consider is neutron degeneracy pressure. This arises from the Pauli exclusion principle, a fundamental rule of quantum mechanics stating that no two fermions, particles such as neutrons or electrons, can occupy the same quantum state simultaneously. When neutrons are packed together at nuclear densities, this principle produces a strong outward pressure. It is this pressure that halts the core's collapse once the star has reached its neutron-rich state. Essentially, the neutrons themselves resist being squeezed any closer, creating a quantum stiffness that counterbalances the gravitational force. Alongside neutron degeneracy pressure, the strong nuclear force plays a crucial role. This force binds neutrons together in atomic nuclei and acts at extremely short ranges, becoming repulsive when particles are forced too close together. In the inner core of a neutron star, where densities exceed that of normal nuclear matter, this repulsion contributes an additional layer of resistance against gravitational collapse. The combination of degeneracy pressure and nuclear repulsion forms a complex network of forces that allows the star to maintain its compact yet stable structure. The interplay between gravity and quantum forces is not static. As gravity pushes matter inward, it increases density and pressure, which in turn strengthens the quantum forces opposing collapse. This feedback loop creates a finely tuned equilibrium. If gravity becomes slightly stronger, for example, if the star gains mass, the degeneracy and nuclear pressures increase to resist further compression. However, there is a limit to this balance. The Tolman-Oppenheimer-Volkoff limit, approximately 2.2 to 2.4 solar masses, represents the maximum mass that a neutron star can support. Beyond this threshold, quantum forces are no longer sufficient to counteract gravity, and the star collapses into a black hole. It is important to note that this balance is unique to neutron stars. In ordinary stars like the Sun, electron degeneracy pressure and thermal pressure resist gravity, but the densities and forces involved are far smaller. In neutron stars, gravity is so intense that it brings matter to the edge of physical possibility, making quantum effects macroscopically significant. This is why neutron stars serve as natural laboratories for studying the interaction between gravity and quantum mechanics, offering insights that cannot be replicated on Earth. By understanding the competition between gravity and quantum forces, we can appreciate why neutron stars exist at all. Their structure is the result of a delicate tug-of-war between the pull of space-time and the resistance of matter at its most fundamental level. Gravity shapes the star, while quantum mechanics ensures that it does not collapse entirely. Together, these forces create one of the most extreme, yet stable objects in the universe, a place where the rules of physics are pushed to their limits, but harmony is still achieved. Gravity inside a neutron star is not only extraordinarily strong, it also produces effects that stretch our imagination and challenge everyday intuition. The interplay between immense mass, extreme density, and curved space-time results in phenomena that are unique to these compact stars. Understanding these effects helps us appreciate both the power and subtlety of gravity under such extreme conditions. One of the most striking consequences of intense gravity is time dilation. According to general relativity, clocks run more slowly in stronger gravitational fields. Near the surface of a neutron star, time passes noticeably slower than it does far away from the star. This effect becomes even more pronounced toward the interior, where pressures and densities are greatest. In essence, an observer on the surface or near the core of a neutron star experiences time at a different rate than someone observing from a distance. This has profound implications for the physics of these stars, influencing everything from the behavior of particles to the emission of radiation. Gravity also dramatically affects light and radiation. The immense curvature of space-time bends light around the star, allowing us to see parts of the surface that would normally be hidden. This gravitational lensing is not only a remarkable visual effect, but also a tool for astrophysicists, helping them determine the mass and radius of neutron stars with precision. Light trying to escape from the interior is severely redshifted, losing energy as it climbs out of the gravitational well. Even neutrinos, nearly massless particles that rarely interact with matter, are influenced by the star's gravity. Their paths curve and their energies shift in response to the extreme environment. Tidal forces inside a neutron star are equally extraordinary. As one moves toward the core, the difference in gravitational pull across even small distances becomes immense. These tidal forces are so strong that they can stretch and compress atomic structures, effectively shredding ordinary matter into a dense neutron fluid. The atomic lattice of the crust is compressed to the point where individual nuclei begin to merge, forming a continuum of neutrons. Gravity here is not merely a force, it is an agent that reshapes matter at the most fundamental level. Another remarkable effect is the trapping of radiation and particles. In the dense interior, photons and neutrinos interact with matter in complex ways, sometimes becoming temporarily confined before escaping. Gravity effectively slows the escape of energy, which influences how the star cools over time. This leads to long-lived heat retention in certain layers, subtly shaping the thermal evolution of the neutron star and contributing to observable X-ray emissions. Finally, the surface gravity of neutron stars is staggering. An object dropped on the surface would accelerate at roughly 100 billion times the rate it would on Earth. Any material in orbit near the surface is subject to extreme tidal stretching and rapid orbital motion. Magnetic fields, often trillions of times stronger than Earth's, interact with this gravity to produce complex magnetospheres and energetic particle emissions, creating pulsars and other high-energy phenomena. In summary, the extreme gravity inside a neutron star transforms space, time, and matter in ways that are entirely alien to our everyday experience. Time slows, light bends, particles are trapped or redirected, and matter itself is compressed into states that challenge our understanding of physics. These effects are not merely theoretical, they influence observations, guide astrophysical models, and deepen our appreciation for the subtle yet profound ways gravity shapes the universe. By understanding these extreme effects, we are prepared to consider the ultimate consequence. What happens when gravity overwhelms all resistance and the neutron star can no longer support itself? In the next section, we will explore the conditions under which a neutron star collapses, bridging the boundary between the densest stars and black holes. Even in the dense, extreme environment of a neutron star, gravity is constantly in competition with quantum and nuclear forces. The balance between these forces allows the star to maintain stability for millions or even billions of years. Yet, there is a limit to what these forces can withstand. When gravity becomes too strong, the neutron star can no longer resist collapse, and the results are both dramatic and profound. The maximum mass a neutron star can support is determined by the Tolman-Oppenheimer-Volkoff limit, roughly 2.2 to 2.4 times the mass of the Sun. If a neutron star accumulates additional mass through accretion from a companion star or merger with another neutron star, it can surpass this threshold. At this point, the internal pressures, no matter how extreme, are insufficient to counteract the inward pull of gravity. The equilibrium that once defined the star breaks down. Once this balance is lost, the neutron star collapses into a black hole. The collapse is rapid and catastrophic. Matter is crushed into an infinitely dense singularity, and the surrounding spacetime curves so intensely that not even light can escape. The event horizon forms, marking a boundary beyond which no information can reach the outside universe. What was once a stable neutron star becomes an entirely different type of object, governed by the ultimate limits of gravity. Before this final collapse, certain observable phenomena may occur. Neutron stars nearing the mass limit can emit intense bursts of radiation or gravitational waves, especially during mergers. These signals carry invaluable information about the star's internal structure and the extreme physics at play, allowing astronomers to study gravity and matter under conditions far beyond terrestrial experimentation. It is important to recognize that while the collapse is extreme, it is a natural consequence of the laws of physics. Gravity does not act maliciously. It simply responds to the mass and energy within the star. The interplay of gravity, pressure, and quantum mechanics sets the stage for these cosmic transformations, illustrating both the power and the elegance of physical laws. In essence, the story of a neutron star is one of balance. Gravity shapes it, quantum forces support it, and the limits of these forces define its fate. When gravity wins, the star gives way to one of the universe's most mysterious objects, a black hole, highlighting the profound consequences of extreme space-time curvature and the delicate thresholds that govern the cosmos. Neutron stars are remarkable windows into the extremes of the universe. In just a sphere barely 20 kilometers across, they contain more mass than our Sun, compressing matter to densities that defy everyday intuition. Inside these stars, gravity is not a simple force. It is the curvature of space-time itself, shaped by mass, energy, and the immense pressures that resist collapse. Quantum forces and nuclear interactions work in tandem with gravity, maintaining a delicate balance that allows these stars to exist at all. By exploring the interiors of neutron stars, we gain insight into phenomena that cannot be recreated on Earth. We see time dilate, light bend, and matter compressed into exotic states. We witness the interplay between fundamental forces at scales both tiny and immense. Every layer, from the rigid crust to the mysterious inner core, tells a story of nature's capacity to balance seemingly opposing forces. Yet neutron stars also remind us of the universe's limits. When gravity becomes too strong, the equilibrium fails, and the star collapses into a black hole, illustrating the profound consequences of extreme space-time curvature. Ultimately, studying neutron stars is a journey toward understanding the universe itself. They reveal how gravity shapes matter, energy, and time, challenging our intuition while inspiring awe. These objects, small in size but immense in significance, invite us to contemplate the extraordinary ways in which the cosmos organizes itself and the delicate harmony that makes it possible. Thank you for joining us on this journey into the extraordinary world of neutron stars and the extreme gravity that shapes them. The universe is full of phenomena that challenge our understanding, and exploring these cosmic laboratories helps us see the delicate balance between gravity, quantum forces, and matter. Share your thoughts and questions in the comments. What fascinates you most about neutron stars or the extremes of the cosmos? Take care and never stop exploring.